Good day class, good everybody. Here you are, welcome to Turning Point tutorial. Here we want to have another section in our topic of redox reaction. Remember last time we need to make we had some definition we had made based on the types of redox reaction definition, and we have just given out 4 of them. Last time we talked about based on the transfer of oxygen, based on the transfer of hydrogen, based on the transfer of electrons, as well as based on oxidation number. But remember, the last one we didn't actually talk about was based on electronegative atoms around an element when moving from the reactant side to the product side. And remember, when you keep on learning different types of definition, it gives you a better way, a better view in this aspect of defining redox reaction. Don't get tired when you keep on learning various ways of defining redox reaction, because in life you need to aspire to acquire what you desire, and when the going gets tough, if you misfire, don't retire but refire. So let's refire to the next section to discover how we can define redox reaction based on electronegative atoms around an element when moving from the reactant side to the product side. Now, based on increase, or you can say in terms of increase, in terms of let's say increase now, in terms of electronegative atom, electronegative atoms around an element. How can we now define our redox reaction? Now, we just start with oxidation. Now, oxidation reaction is the increase in the number of electronegative atoms around an element when moving from the reactant side to the product side. Once again, I said oxidation is defined as the increase in the number of electronegative atoms when moving from around an element when moving from the reactant side to the product side. Now, what about the aspect of reduction reaction? Reduction reaction is the decrease in electronegative atoms. The decrease in electronegative atoms around an element when moving from the reactant side to the product side. Let's consider that of the oxidation, because we are dealing with based on electronegative atoms around an element. Examples of electronegative atoms, we talk about chlorine, is one of them. We talk about chlorine, we also have fluorine too. We also talk about that of, let's say, oxygen, as our electronegative atoms. We talk about bromine. And let's now see a good example here in the aspect of when we discuss the increase, or I say increase, or I say decrease. Increase in the number of electronegative atoms around an element. Let's see this. For instance, we have, let's say we have like this here, magnesium chloride. You can see magnesium chloride, something like this. And then when you have an addition here, you talk about something like this, magnesium like this in the case. Now, I just make an illustration to make it clearer. Or we can come to another form, we can bring it this way, very way. You see zinc chloride, and you have an addition, so make it like this, and then it becomes like this, zinc like this, chloride like this, and then in the very aspect, there's an increase. This right here, we have only 2 chlorine, but right here, we have 3 chlorine. Right here, we have 2 chlorine, we have 3 chlorine. There's an increase in the number of electronegative atoms around this chlorine, and around the magnesium. Magnesium is actually the element now. So the number of chlorine, which is the electronegative element around, electronegative atom around this magnesium, is just 2, but at the other side, it's now 3. It's an increase. That is what kind of reaction is this? It's called oxidation reaction. It's very clear, the same thing here. Moving from this side to this side, this oxidation. But once there's a decrease, then we call it reduction. Let's see in the other way around, if we have, let's say, zinc very form, and there's a decrease. Let's go in this very way right now. We can see let's say reduces to something like this. Let's say zinc, right, and then like this, and there's a decrease. When you balance it up, you see you can balance the equation. But let's say right now, from this side to this side, there's a decrease. Now what's the decrease? Now this one is a reduction. It's a reduction. Now when we decrease in the number of electronegative atoms around the zinc, when we from the left to the right, from the reactant side to the plus side, that is what we need to know. But just that's one of the definitions we couldn't touch last time. But now we want to go to the other aspects, which is very important. An important aspect, which is oxidizing and reducing agent. Oxidizing and reducing agent. Now we will consider this today, the oxidizing and the reducing agents. What you should know about an oxidizing agent and what you should know about the reducing agent. What is an oxidizing agent? An oxidizing agent is an electron acceptor which causes a co-reactant to be oxidized in a reaction. Once again, I said oxidizing agent is an electron acceptor which causes a co-reactant to be oxidized in a reaction. Now, for example, let's see the different examples of oxidizing agents. We have the non-metals. We also have non-metals like oxygen. We also talk about the halogens. These are examples. Non-metals like oxygen is one of them. Let's see, the oxygen is one of them. We also have the halogen. Remember, we're talking about oxidizing and reducing agent. Oxidizing, and reducing agents. Oxidizing and reducing agent. Now we see that oxygen is one of the oxidizing agents. The oxygen is there. Also have the halogen like the fluorine, like the chlorine, like the bromine, and the iodine, and so on and so forth. Now, these are examples of what? The oxidizing agent. Then we also have more examples of oxidizing agent, which we should consider very soon. But for the halogens, you should know that the oxidizing ability of the halogens will decrease down the group in the periodic table. Normally decreases down the group. The oxidizing ability of the halogens normally decreases down the group when you are considering it from the periodic table. As if from fluorine to bromine to iodine, something like this. That means it's from this to this, and then from this to this, then like that to the iodine. That means the ability to actually act as an oxidizing agent. Fluorine can do that more than chlorine, and chlorine more than bromine, and from bromine then more than the iodine. Now, for this reason, we can now say that halogen displaces another. A halogen can displace another halogen below it in the periodic table from a salt of that halogen in its equation or in the aqueous equation. Or you can say, sorry, in aqueous solution. I am saying it right here again that a halogen can displace another halogen below it from a salt of that halogen in aqueous solution. Now, let's give you an example here. For instance, you have the fluorine plus, let's say fluorine plus potassium chloride. Now, when you react, you see fluorine is more kind of more of an oxidizing agent than chlorine, because fluorine is under fluorine. Now it means that fluorine has a right to displace chlorine to form what? To form potassium fluoride, and then you have chlorine actually staying on its own. But in the case of now bromine, now let's say for example now bromine reacting with potassium chloride, there's no reaction will occur at all, because right here you know that from the periodic table chlorine is higher than bromine, so that's not possible. Now, more examples of oxidizing agents are: one, we have the acidified KMnO4, acidified potassium tetraoxomanganate. 7 as KMNO4. KMNO4 is one of the example, or you can write, or you can say MNO4 ion acidified KMNO4 or MNO4 ion. Number 2 is acidified potassium heptaoxodichromate 6, that is K2CR2O7, or you can say the CR2O7 ion. This is another example that you can see acidified one. Then you also have more example like the conc H2SO4, the concentrated tetraoxosulfuric acid. The conc H2SO4 is an example of an oxidizing agent. Then you will see conc, we have the conc HNO3. Conc HNO3 is an example of an oxidizing agent. More other examples are MNO2, like the manganate 2 oxide. We also have MNO2 examples of oxidizing agent. We also have ozone. Ozone is O3. Ozone O3 is an example of oxidizing agent. We also have iron 3 salts. The iron 3 salts, all iron 3 salts are examples of oxidizing agents. Iron 3 salts are also there. These are examples of oxidizing agent. We also come to the other aspect, which is reducing agent. What is a reducing agent? A reducing agent is an electron donor. It's an electron donor which causes a co-reactant to be reduced in a reaction. It makes its co-reactant to be reduced in a reaction. Now, examples of reducing agents are all metals. Then also have metallic ions like iron 2 plus, lead 2 plus is there. We also have tin 2 plus. These are examples of the reducing agents, and some non-metals also. Some non-metals like carbon. Carbon is also a reducing agent. Hydrogen is also a reducing agent. Then compounds like carbon 2 oxide are reducing agents too. And we also have this compound lithium tetrahydroaluminate 3, which is LiAlH4. We also have that now again, sodium tetrahydroborate 3. Right now we have this one too. It's another reducing agent. We also have hydrogen sulfide. Hydrogen sulfide is another aspect. Hydrogen sulfide. We also have another one again, iron 2 salts. All iron 2 salts are also examples of reducing agents. All iron 2 salts are there too. Then also have, let's just add this one to it, hydrogen sulfate, H2SO3. These are examples of reducing agents. Now, some substances can actually act as both oxidizing agents and reducing agents. Some of them can act as both oxidizing agents and as well as reducing agents. Substances like what? Those substances are, let's give two examples, like SO2 and as well as what, the hydrogen peroxide, sulfur oxide and hydrogen peroxide. These are examples of substances that can act as both oxidizing agents as well as reducing agents. Now, the role of such a substance actually plays the substance plays in a reaction depends on the oxidizing or reducing ability of the co-reactants. You can see here the reason why we have such substances is because the role of such let's say substance that can act as both oxidizing agent and reducing agent because of the ability of the co-reactants to actually act as oxidizing or a reducing agent. If the co-reactant can act as a reducing agent, then that substance will act as oxidizing agent. But if the co-reactant is acting as an oxidizing agent, then that substance will act as a reducing agent. So that's what we can consider here. It means here, let's say an example right now. We say in the case of, let's say, sulfur 4 oxide reacting with, let's say, a compound like oxygen, a molecule like oxygen. Once look at this reaction right now, once the reaction goes on, what is information, what is formed, this is a kind of reaction. You see here that the sulfur stays on its own, that is actually being reduced. Sulfur 4 oxide being reduced to sulfur, and then you have the other aspect, oxygen stays here, and then you consider this reaction. That's what's going on here right now. From here to here, what you consider is reduction reaction, and right from here to here is what you have to consider it as what oxidation reaction. Right now we say that this, in every case, What can we say about sulfur 4 oxide? Sulfur 4 oxide is not acting as the oxidizing agent, because it's the one that gives out the oxygen to the oxygen molecule, and so it itself is being reduced to become sulfur, while the reducing agent is right now, in the very case, the reducing agent right now is now known as oxygen. Now, because you consider it very well, oxygen is not acting as a better oxidizing agent in the very case. Oxygen in this very reaction is acting as a better oxidizing agent. Therefore, sulfur 4 oxide will not act as oxygen, is acting as a better reducing agent. Therefore, sulfur 4 oxide is not acting as the oxidizing agent. Why? Because oxygen is removing oxygen from sulfur 4 oxide. This oxygen is not acting as a better reducing agent, because it takes away this oxygen from sulfur 4 oxide, while sulfur 4 oxide is not acting as the oxidizing agent. So here you can say yes, SO2 is the OA, while the oxygen is the ROA. But in the case of SO2 reacting with the hydrogen sulfide, what is the end of the reaction? In the very case, you can see here that SO2 reacting with hydrogen sulfide. What can we say about this? We can say that the oxygen is right here acting as, let's say, hydrogen sulfide reacting with sulfur 4 oxide. Look at the reaction now. We have that sulfur is actually stays on its own and the water is formed. Now let's come back to this very aspect. Now looking at it very well, make a correction here. We have sulfur 4 oxide reacting with oxygen. When sulfur 4 oxide reacting with hydrogen sulfide, what is the product? And what is formed is water. Water is formed. Now look at this here again. Sulfur 4 oxide reacting with hydrogen sulfide, water is formed, and then so from here to here there's reduction, and right from here to here is oxidation going on here. Now you can see hydrogen sulfide is acting as a better reducing agent, while the oxygen sulfur 4 oxide is acting as the oxidizing agent. So this oxidizing agent, while here is the reducing agent. Now we have in the other aspect, what if we consider SO2 reacting with O2? What happens in the very case? What if we consider SO2 reacting with O2, and then you have it to be you have SO3 formed? What now can we say? If oxygen joins itself to this, then we can say right now that the oxygen is not acting as a better oxidizing agent. The oxygen is not acting as a better oxidizing agent, while the sulfur 4 oxide is not acting as a reducing agent in the very case. So we can see here that it depends on the ability of the co-reactant to act as oxidizing agent or as a reducing agent. Now, if you consider all these reactions, we can give the various reactions to back this thing up to actually give us a better clarification on this very aspect. Now, once again, I say here, some substance can act as both oxidizing agent and reducing agent. While some are acting as reducing agent, the others are acting as oxidizing agent. Now, we want to consider another aspect. Another aspect to consider, which we will see in the next section of this teaching. So we'll just wrap it here. Let's move on to the next aspect of this topic of redox reaction. Thank you very much. We'll talk about this better. Now we want to proceed to the other aspects, because we have just looked at the area of the oxidizing agent and the reducing agents. Now we come to the next aspect, which is very, very important. We should not actually overlook this, and that is nothing but oxidation number. Now, what is oxidation number? It is also known as oxidation state. It refers to the charge a substance possesses, either in its combined state or free state. Oxidation number is defined as the charge a substance possesses, either in its combined state or free state. Now, you should know quite well that there are rules that govern oxidation number that will help us to actually know how to calculate oxidation number, and the rules are very, very simple, just very simple rules to follow. and we see them one by one. But let me just make you to understand right here, and when we are done with these rules, the next thing we do in the next class to come is to answer various type of questions under the calculation concerning oxidation number, as well as how to distinguish what we have been learning since, how to distinguish oxidizing agent, reducing agent in a reaction, and how to actually understand which kind of reaction is not on kind of redox reaction, and then how to know the ones that are redox reaction. But let's now come to the rules that governs the calculation of oxidation number, or the calculations in oxidation number. What are the things we should know before we can continue to talk about the aspect of oxidation number calculation? Now, the first rule here is that number one, the oxidation number of an element, of the atom of an element at free state, or can say at combined, at a free state or at uncombined state, is always zero. Is always zero. Mention any element at free state or in its uncombined state. For example, you talk about sodium in its free state. We talk about potassium in its free state. We talk about calcium in its free state. We talk about, let's say, a non-metal like chlorine in its free state. They are all having zero, nothing on top. There's no charge. It doesn't carry any charge. By this time, it's in its free state. It has just zero. There's nothing like say it has a charge written on top and above it. No, then it's always zero in that very case. Then number two, the oxidation number of the sum of all atoms of an element that come together to form a compound is equal to zero. For example, you consider any compound. Let's mention a compound like H2SO4. H2SO4 is tetraoxosulfuric acid or hydrogen sulfate. Now, there's nothing like, now when you consider the element, the atoms that form, the atoms of hydrogen, the atoms of sulfur, the atom of oxygen, two atoms of hydrogen, one atom of sulfur, and four atoms of oxygen combined together to form this compound, and there's no charge written on above it here. It means that the oxidation state is zero. So you just write zero, or you can say equal to zero. Then, like in the case of sodium chloride, this is a compound, and there's nothing like charge written on top. So it has an oxidation state of zero. But that's one of the things you should know, have in mind here in the very case. Then the next one, another rule to follow is that the oxidation number of an atom in the form of an ion is equal to the charge it carries. Is equal to the charge it carries. Let's see an example here to make it clear in the very case. Let's say this is an atom. Let's say it's an aluminium. But what is the ion of aluminium? Aluminium 3 plus. Aluminium ion is written this way, and then what is now the oxidation number is equal to plus 3. In the case of chlorine ion is Cl minus. What is the number of oxidation? The oxidation number is minus 1. Then the other aspect of, let's say, nitrogen, or we can say in the case of calcium 2 plus. What's the oxidation state here is plus 2. Now in the case of oxygen, the ion is O2 minus, and the oxidation state is minus 2. So we can say the next one, another rule to follow is that in the case of, let's say, the radicals, we pick up the radicals. Now, whenever you consider the oxidation number of the sum of all atoms that make up a radical is equal to the charge that radical carries. We have different radicals. Like now, this is a radical. We say we have let's say SO4 2 minus. This is a radical, and the charge it carries, we have minus 2. As well as this is another one, minus 2. And in the case of CO3 2 minus, what's the charge? This is a radical, and the oxidation state here is also minus 2. In the case of PO4 3 minus, then we can have it as minus 3 as the oxidation number. Then in case of, let's say, O minus, this is a radical, so this has minus 1 in the very case. Now we have to understand we have various types of radicals. Radical examples of radicals to consider and the state of oxidation. Now here we have a radical. This is a radical. These are examples of radicals, and then we have their oxidation number. Oxidation number right here to consider. If we consider all the radicals, like which one? Let me give you a more example. We have seen that of SO4 2 minus. What is the state of oxidation? -2. In the case of CO3 2 minus, here it has -2. In the case of SO3 2 minus, it's -2. In the case of NO3 minus, it's -1. Then in the case of cyanide ion, it is actually -1, 2. In the case of hydroxy ion, is -1. Then in the case of, we have others like the chloride ion is -1. They also have, let's say, chloride ion, chloride 5, we have CO3 2 minus, ClO3 minus is -1. We also have the others like, let's say, that of NO2 minus is -1, and so on like that. We have different examples to consider when it comes to this aspect of the different radicals. All the radicals have their charge written on at the top, and the charge written on top is the same as their individual oxidation number. Now we come to another rule to follow. Look at oxidation number of hydrogen, the special case. Hydrogen in its combined state is always +1. It has oxidation number of +1. As is for hydrogen, is +1 in its combined state. But when you come to, in the case of in its combined state is plus, but in a combined state, when it comes to the case of combining with a metal, that is example metallic hydrides, metal combination, when you combine with a metal to form metallic hydride, like for example of, we have sodium hydride. This is a metallic hydride. We also have let's say in the case of calcium hydride, this is a hydride too. Now this is when calcium combined with metal to form metallic hydride. Then it will have -1 as the state of oxidation. Now then in that very case, hydrogen will be -1, not +1 again. Then if you consider in the case of oxygen, another special case to look into, the oxidation number of oxygen is actually in its combined state is -2. It's -2. Except in peroxide, it's always -2. Let's say, for example, we say peroxide, I mean, let's general formula, you have XO2, it can be, let's say hydrogen peroxide, can be sodium peroxide, and go right now, and we can also say, like in the case of other peroxide, consider the oxygen here in that state, because in its combined state, oxygen is always -2. But when it comes to the peroxide, oxygen then will become -1. That is the state of oxidation. Then we can write that oxygen is, in the case of the peroxide, oxygen is always having -1 as the oxidation number. Then in the case of let's say all the elements in group 7, the group 7 element will form ion. The ions formed by the group 7 element, their oxidation state is always -1. Then that of the nitride, like nitrogen combined with nitrogen is nitride, anything nitride, you have nitrogen N3 minus is always, then in that very case is always -3. Then the other aspects, let's say consider in the case of sulfur. Sulfur and oxygen have the same state of oxidation. Sulfur in its combined state is always -2. The same thing with oxygen in its combined state is always -2, except in the peroxide. Then in the case of nitrogen combined with another element or another atom, you have a nitride. Then nitrogen will be -3. All these are the different types of oxidation states. Now, having known the different oxidation states, you can now boldly come to the calculation aspect, which we'll see in the next class. You can talk about the calculations involving that are bearing in oxidation number, different type of calculations, varieties of calculations, as well as how to know which one is reducing in a reaction, whether it's reducing from moving from reactants to products, or from in any reaction you consider. Now, we generally have to go through once again what is it all about. We have known that an atom in its free state is always equal to 0. That is the oxidation number. In the case of all the elements put together to form a compound, that compound on its own we have 0 as the oxidation state. The same. Then in the case of that of an atom that carry a charge, that is, anytime you see an atom carrying a charge, it's no more called an atom, it's called an ion, whether positive ion or negative ion. The charge it carries is always that oxidation number 2. Then in the case of the radicals, all the elements that come together to form a radical, they become one. And we have seen a list of different radicals. A list of different radicals we have considered from this table. SO4 2 minus, it has the oxidation state to be minus 2. That of CO3 2 minus, the oxidation state to be minus 2. Then SO3 2 minus, the oxidation state to be minus 2. NO3 minus is minus 1. Cyanide ion is minus 1. Hydroxide ion is minus 1. Then the chlorine oxide ion is minus 1. Then this one is minus 1, and so on and so forth. Then we are also seeing that the group 7 ions, the ions formed by the group 7 element is always minus 1. We also see in the case of nitrite is minus 3, that the nitrogen is always minus 3. Then in the case of oxygen in its combined state is always minus 2, except in the peroxide. Then in the case of hydrogen in its combined state is always then plus 1, except in the case of the metallic hydride. We have seen various oxidation states. Then in the next class, when we meet, we'll talk about how we can handle the calculations during in the aspect of oxidation number. Then I want you to go prepare yourself so that you prepare, read ahead, because as we get through the calculations, we move straight into the aspect of the balancing of a redox reaction, how we can balance redox reaction. And then you have the principle, the steps to follow. Then we'll consider if it's going to be in acidic medium or alkaline medium, or neutral medium. And when we get all these things completed, we can be sure we can handle questions in either external exams like the WAEC examination, NECO examination, or you can see the UTME examination, or even the post-UTME examination. You can fully be sure to get through with all the questions and the answers without any confusion and without any doubt. This turning point tutorial, once actually you get anything difficult, you always remember that you need to aspire to acquire what you desire, and when the going gets tough, don't retire in any form, but refire, and you get to the top. See you at the top. Don't always forget to call us, call our number, or you can actually chat with us in our WhatsApp, and then you can also meet with us face to face to get clarification in different aspects in chemistry or in physics, in all other subjects, and then you get yourself loaded to get to the top. See you in the next class.